Okay, perfect.
So
Okay. So I think, Luis, I will just briefly introduce everybody quickly. Let's start officially the final presentation of the PDEng software technology. The generation is 2019. So from January next year, they're going to work on their final graduation project to get a degree on doctorate in engineering doctorate. And today, Luis Mancilla will give the next talk to give the objective of the project, and he's one of the main main clients to give an assignment for us. We also worked with Christoph Bonwald, who is the head of the software technology section at the European Space Agency. And this is the PDEng software technology program collaborating for the third time with the European Space Agency. And we are very proud of our collaboration, and for sure it's not the last one. So after the Luis presentation, the project manager, Juan van der Heijden, will start the presentation. And at the end, we have a privilege and actually an honor to welcome Claude Nicollier, the first and only astronaut from Switzerland to fly to the space. And he will also give the importance of this research and development activities. And at the end, we will have a Q&A section with the people in attendance. And of course, the presentation is being live streamed on YouTube and will be also online. Okay, so Luis Mancilla, the floor is yours.
okay, thank you. Thank you, Janja. So it's gonna be quickly, just a few words. So I just wanted to introduce a little bit the context of the activity. So which is the objective of the activity, and the objective was to design and implement a system that could detect on board the different emotional states of the astronauts. And for that, we wanted to explore the possibility of applying artificial intelligence, and more specifically, supervised methods, machine learning supervised methods. The duration of the activity, it was only 2 months, and I think it's important to that number, because that helped us to give the correct perspective to the work that has been done over these 2 months. And as I just said, the activity was carried out by a group of students from the University of Eindhoven. Unless Christoph has something else to add, I will leave the floor for the team. Just a few rules. So I think I recommend everyone to mute during the presentation, and unless you are speaking, it would be nice if we switch off the videos, saving some bandwidth. And that's it. Christoph, do you have something to add, or?
Yeah, just looking for the unmute button. So thank you, Luis. So no, I think it was very clear. So I think the topic was very interesting, and I'm very kind that the students have done so much effort. I should keep that for the end of the presentation, but thank you very much, and I'll let you the floor.
Great, thank you all. Welcome everyone to the presentation of our final project, the Stern Astronaut Emotion Recognition System. My name is Juan van der Heijden, and I was the project manager for this project. Thanks for the nice introductions. Last things I want to add is indeed, please turn your cameras off for the bandwidth issue, and also keep your questions unless they are very burning and urgent. Till the last moment, we'll have a nice Q&A session. So let me first go over the topics of today. First, we'll have a very nice introduction on who we actually are as the PDEng software technology. Then we'll go into the problem statement of the project. Then we'll go over the global architecture. Then we go more in depth in the video architecture with a demo. Then we have the audio architecture with a demo. And we'll wrap it up with the verification and validation and a conclusion. So starting off with who we are. As we told, we are the PDEng software technology, but when we say PDEng, it doesn't always ring a bell for everyone. So to explain it, let me go through a normal path in academia in the Netherlands. In the Netherlands, for the first 3 years, you do a Bachelor of Science, which is followed up by a Master of Science. And after your master, a lot of people go into the industry or continue in academia. And a regular path that you normally take is to do a PhD, which is a doctor in philosophy. Then you do a detailed research in a specific topic, and you write a lot of papers about it, and it's quite theoretic. On the other side, you also have the PDEng in the Netherlands, which is a professional doctorate in engineering. And this program is really a traineeship for designers, and we really prepare everyone for the industry. So we do this by doing multiple training projects. So in the first year, we have 3 large training projects for larger and middle-sized companies and organizations. And this project is an example of that. The PDEng takes 2 years, and that's who we are. Since the PDEng and the PhD are both doctorate programs, you can also put them into perspective a bit. And we like to do that with this graph. And you see on the bottom part, we have the PhD, which is more to the fundamental side, and it's quite curiosity driven. And the PDEng is more pragmatic and also application oriented, which also shows in the work. And we'll make that clear by the work that we actually provided in this project. So that's a short introduction on who we are. Let me go into the problem statement of this project. Astronauts, while they are on a mission, they can often be very stressed because they're in a stressful environment. They have to constantly perform at their highest potential. This can lead to very heavy emotions, either positive or negative. And it shows that these heavy emotions can be quite impactful on the success of a mission. Additionally, due to the far distance, assessing an astronaut's emotional state is quite difficult in person. Even now already, when there is contact and you can ask an astronaut about their emotional state, it's often delayed. And if we even look ahead a bit in deep space missions, then there is no contact at all. So taking these 2 problems, ESA actually came up with a project proposal for us, which is to develop an emotion recognition system. Now what that means is that we monitor an astronaut and we use their video and audio streams to assess what their emotional state is. And we do this by using artificial intelligence. And this is the project that we worked on. Of course, the project always comes with some challenges, and I would like to go over these challenges one by one. Our first challenge was that this was quite a new domain for us, artificial intelligence. Our second challenge is that we had limited resources. Our third challenge is that we had a short time. Our fourth challenge is that we were dealing with open source datasets and software. And our last challenge is that we were working remotely due to the pandemic. You probably heard that more often in the last months. I want to go over these challenges one by one, starting with artificial intelligence. And since we have a very broad audience today, we're also live streaming to YouTube. I want to briefly introduce AI on a really abstract level. Please take into account that some details might be a little bit inaccurate, just to keep it abstract. So artificial intelligence really is a different way of writing software as a traditional way of writing software. Traditionally, we write algorithms and formulas, and then we let a computer execute these algorithms. But in AI, we really want to teach a computer how to interpret certain input and how to give certain output. So we use this comic as an example where the person shows a picture of a car to the robot, and the robot says it's a butterfly. And then the person corrects the robot, says, no, this is a car. And eventually the robot knows, okay, I'm dealing with a car. And it can recognize some characteristics of the picture that it recognizes as a car. And this is kind of the same way that we teach children how to interpret certain outputs by correcting them. Well, this is of course very abstract. Let's go a bit more into detail. So what we see here is on the left, we have a picture of a cat. And we want to use AI to classify whether we see a cat or a dog on this picture. In the middle, we have an AI model, and this is specifically a neural network. And in this neural network, we do all kinds of computations. And on the right, we see our output. So what we do on the left is we take some characteristics out of this image, which can be anything. It can be color, it can be positioning, and we use these inputs into our neural network. And our neural network does all kinds of computations. and eventually spits out a result. When the result is wrong, for example, the AI model predicts that this is a dog, then we correct it. We say, no, we expected a cat. Please alter your equations a bit. So we change the weights of this neural network. And this is a really brief, abstract overview of what we do with neural networks and with AI. And you might think, how does this compare to our research that we're doing? So if we change the input from a cat to an actual video stream or an audio stream of an astronaut, we can use that as an input to our neural network. And in the same way, do computations and not classify whether there's a cat or a dog on the picture, but classify the emotion of the astronaut. For example, here, neutral, happy, sad, angry, or fearful. So in the same way, we use the input from the astronaut, we do some computations, and if the AI model gets it wrong, we try to correct it. And if you do this iteratively and long enough, then you get pretty good results about the emotional state. You see this AI model is not always the same shape or form. It can be very long, it can be very wide. And when we're dealing with large neural networks, we call this deep learning. And this is actually what we're doing. So artificial intelligence was quite a new domain for us. We only had 2 trainees with a background in data science, and the rest were, so to say, regular software engineers. And this was one of the first projects for many of us to deal with AI. So this was quite a challenge at the beginning. The second challenge that we were dealing with is limited resources. We know that eventually we want to deploy our system into a spacecraft. And we're very aware that this won't be happening on a Raspberry Pi, but it will be on a chip. However, we want to kind of mimic this situation of limited resources by using something like a Raspberry Pi. So that's why we chose this for the short time span. And here you can see the specs of it. The challenge in this is that we must really optimize the model and make sure it runs on a resource with computing power, so to say. Then up to our third challenge, which was the short time. We have a 10-week project, so that's pretty short. And even 1/4 of it are used by PDEng activities. We have all kinds of courses and workshops in between, all kinds of impediments. So if you really think about it, it's a 7.5 week project of what we really work on. A fourth challenge was the open data set and open source software. This really limits us in our choices. We can only use open source with the right licensing. So some data sets are limited to us and some kind of software are limited to us. And the last point was the remote work due to the pandemic. Of course, we have the issue with communication and with distractions when working from home. We were quite a large team, so communication is quite an issue. But also we had some hardware components, as mentioned before, like the Raspberry Pi. And sharing these hardware components was a bit harder because they also have sensors, we have to use them. So just making them available online was not enough. So this was also a challenge for us. And now I wrapped up the challenges and our goals of the project. I want to give the word to Chris to talk about the technology stack and the global architecture.
Thank you, Juan. So I'll start with the technology stack. Basically what this is the different type of libraries and frameworks that we used in the development of this project. So most of our programming was done in Python, and we used several different libraries, including TensorFlow and OpenCV. These are generally used for computer vision and other machine learning tests. Librosa is used for some of the audio detection and how we actually get the information in and structure it. OpenVINO is a optimization platform, and dlib is also used for certain face detection and characteristics for mostly face alignment, things like this. So also, it might be interesting to tell you about our training environment. We do have personal computers, and they have CPUs on them, so we can do some of our training, our machine learning training on the computer if necessary, mostly if it's for prototyping and setting up, making sure that our inputs and format and structure can compile properly. The DOE also has a high-performance computing cluster, so you can think of this like a supercomputer where we have Tesla V100 GPUs that we can use. And then we've also done some cloud training with Google Colab, which uses Tesla K80 GPUs. So basically, we have different ways that we can get our results and do our training for our models.
Roger, please.
What? Okay. So on the global architecture goals, we go back and we look at our objectives. So we're trying to develop an emotion recognition system, and this system needs to use AI to classify different emotions. And the way we're going to do that is we're going to use this Raspberry Pi. So we're going to take in, we have a camera screen, which is our visual sensor, and we have microphones. So this is our audio sensor. And we still have our challenges, which are, this is a new domain for most of us. We have hardware constraint, which is this Raspberry Pi. So this embedded system needs to reflect the limited resources that can be used initially in a space project, and need to do this in 10 weeks, and it needs to be using public and open data sets and software. Okay, so now that we have this idea of designing a system that will be used in deep space, which is more than a few years away, we have to think about how we can do our architecture. So effectively what we've done is we've created two pipelines. We make a video pipeline for the camera to take the facial features and these different images from the face, and an audio pipeline. So this is actually going to look at the speech components of your voice. And there are different data sets for each of these type of inputs that we can use. And some of the data sets actually will have labeled information for both of them. So we identified the data sets that we want to use, but we need to do some pre-processing. So we have this data wrangling module. And what this data wrangling module does is it's actually going to pre-process this information and get it into the right format for the AI modeling. Then this is going to go into our AI modeling module, which is effectively the training and evaluation and optimization of our AI models based on the feature extraction and the hyperparameter tuning. So before we continue, let me give you a little more information about our data sets. So on the left side, you'll see an example from one of the data sets we've used called RevDes. It has actually 24 different actors in it. They're actually actors, and they actually give some different facial expressions and speech different tones when they talk. So the way we initially broke it is we actually took 80% of our total data, just from each actor randomly. 80% went into training. So we try to use this much for training, and then we use 10% for validation and 10% for testing. The idea is that you want to have your training set and your testing and validation sets separate so that you can try to minimize the bias and actually see, does the training itself of the model, will this reflect on the testing and validation? So you want to make sure that your results are, if you just get your results on the training, you might get very good results, but then it doesn't perform well in real life. And even with this distribution where we take 80% of the information from all 24 actors, and we didn't feel like we got some good values, but this wasn't really exactly matched to our use case, because we want our models to generalize better on new data, because aSTronaut is not one of the actors in the data set. So let's try a different approach. Here we actually split our data set based on the actor. So because the RevDes data set has, for example, 24 actors, we're actually going to take 80% or about 20 actors. We're actually going to train our model completely on them. So it's going to look for the anger, fearful, happy, neutral, and sad emotions in this data set. Then for validation and testing, we're actually going to apply this on 4 new actors that the model hasn't seen before. And what this will do is it will give us a better use case that will match the real use case of using this general data that we've created, this general model, and applying it on a new data set, on a new actor too. So the new aSTronaut. So to give you a little more information about the data wrangling, we have our data sets as inputs, and initially we have to do some data segmentation. And what this means is if we have labeled data, so we have audio data and we have video data, we can split them into data sets, little smaller sets that we can actually do separate pre-processing on. This is sent over to our pre-processing submodule, in which things like data cleaning, this is inputting missing information, data integration, which is the combination of multiple data sets or multiple of the same label. This will also conduct the data transformation, which is kind of a normalization or other type of things that you can do to change your data. Or we can also do data reduction. And this is actually something like we can remove some of the data if we don't need to. For example, we have 5 emotions that we're detecting here that was our final distribution. But originally the data set for RevDes has 8 emotions. we have to actually look to see which ones are relevant and which ones will provide the most value. What is the emotion we're trying to? And each one of these, this is an extensible and a modular approach. So some of these different items can be turned on or turned off if necessary. After this pre-processing is complete, we will actually do our data splitting, which is where we split into our training, testing, and validation sets. We try to make sure that all of our interfaces are well defined and that the format that is output by each of these modules is clear so that we can have interoperability between modules. We can actually change out the pre-processing steps without changing the output of each of these modules. Once that's complete, we can send it over to our AI modeling module. We start with the training set, and we actually are going to do our model engineering. So this is kind of feature engineering and our hyperparameter tuning. We actually try to get the best model possible. So we want to get the highest metric results. And once this training is complete, we're going to do some model evaluation. If the model evaluation works really well on the test and the validation sets, and it passes a certain threshold that we have set internally, we can package this model and be prepared for deployment. However, if it's not, we can actually send this information back down to the model engineering, do our hyperparameter tuning, or look at the results and see why it's not working as well as we expect. And then we will keep evaluating this until we get the result that we want. Once it's been packaged, we will send this over for optimization, depending on our optimization method, to try to improve the performance and the execution time on the hardware. This will be sent back to the model packaging to ensure that the output format is exactly what we expect for our deployment module. So these are the high level or global architectural steps that we have. We start with some data set. We want to do some pre-processing and data wrangling, and then we do our training on the AI for the AI modeling. The deployment will come later, and at this time we're going to actually go over to the video steps. So this is going to give you a more in-depth step look into what is conducted for the video processing, and Yusrael is going to take over at this time.
Yeah. Thank you, Grace. I'm Yusrael, and my role is the software architect for the video module in this system. First of all, I'm going to explain more about the dataset that we use in this video module. Our main dataset is RAFDES, and it contains 24 actors with 12 female and 12 male. We have also an additional dataset called CRIMADI, and it contains 91 actors with 43 female and 48 male. From these two datasets, we took only 5 emotions according to our need in this project. Now we go to the data wrangling step, or we can also call it pre-processing. In the video module, we have in total 5 steps. The first step is to extract the frame from the video or the live streaming. And after that, detect the face part of the image. And after that, align the face. And then we take the spatial part of the face. We consider this part as the most important part for detecting emotion. Last but not least, we convert the color into gray color and also changing the size into 32 by 32 pixel. Next is the AI modeling step. So along the way, we tried several architecture for the audio module, for video module. And then we found out that there are 2 most promising for the architecture, which are 2D-CNN and also 3D-CNN. For 2D-CNN, as you can see from the image, it expects only 1 image as an input. For 3D-CNN, it expects sequence of images as an input, or we can also call this sequence of images as video. Therefore, 3D-CNN really suits our need in this project, since we have video or live streaming as an input. Another thing about 2D-CNN is that it has some best practices. Some of them are GoogleNet, AlexNet, ResNet 50, and also MobileNet V2. We did some experiments with them. As a result, a MobileNet V2 gives the best accuracy and also prediction time for our case. That's why we take this architecture as the representative of 2D CNN. In addition, MobileNet V2 was also built for edge device. That's why it really suits our need in this project, since we are going to deploy our model in Raspberry Pi. On the other hand, for 3D CNN, unfortunately, there are not many best practice architectures that adopt 3D CNN. That's why if we want to go with this architecture, we need to build it from scratch. Here you can see that a brief view of the architecture of MobileNet V2 and 3D CNN. As you can see from the image, for MobileNet V2, it has more complex architecture. The reason is that because this is a best practice architecture, and then it covers more cases than 3D CNN. For 3D CNN, it has linear architecture because it covers only according to our need. We tailored our architecture according to our needs. That's why it has linear architecture. We also did some experiments with the pre-processing. In the y-axis, you can see the test accuracy. And then in the x-axis, you can see that the pre-processing that we conduct. The green line shows the 3D CNN model, and the blue line, it shows the MobileNet V2. There are two conclusions that we can take from this graph. The first conclusion is that the more pre-processing steps that we add, the better the accuracy will be. Of course, there is a trade-off here, which is the performance, because if we have more pre-processing steps, it means that it demands more performance. The second conclusion is that 3D CNN shows a better accuracy than MobileNet V2. And again, there is a trade-off there, which is the performance. Since 3D CNN expects a video as an input, it processes and predicts the emotion longer than a MobileNet V2, where it only expects a single image as input. From our experiments, we can conclude that into this single slide. So for MobileNet V2, it has a benefit there in the prediction time, since it only digests single image and predict the emotion based on that image. And another advantage of MobileNet V2 is that the development time, since MobileNet V2 is a best practice architecture, there are a lot of references out there, and we can even use an existing model in our library. Unfortunately, for the 3D CNN, there are not much that the architecture. That's why it will take time to develop the architecture with this approach. For the accuracy, 3D CNN has the advantage here, as we already saw from the graph that 3D CNN shows a better number than MobileNet V2. Also, for 3D CNN, it expects video as an input. It becomes also another advantage, since in this project, we digest video or live streaming as an input. For the model size, 3D CNN is also linear than MobileNet V2. The reason is that for MobileNet V2, this is a best practice architecture and it covers a lot of kind of situation. But for 3D CNN, we tailored it by ourselves. That's why the architecture becomes linear than MobileNet V2. As we know that 3D CNN has this weakness, which is the prediction time. However, we found a solution for that, which is the optimization. We optimize our model by using an optimizer called OpenVINO. And also, when we deploy our 3D CNN model into Raspberry Pi, we use an optimizer called we use a compute engine called Neural Compute Stick 2. With these two components, as you can see from the number, it has increased the performance. That's why we consider the prediction as not the weakness of 3D anymore. That's all about the detail in the video module. Now we are going to show you the demo of a video module. In this demo, it will show you how to configure the system, how to run the system, and then how the system shows the prediction result.
Welcome to the demonstration of the video-based emotion recognition module. In this video, we will show you how you can use the Stern video tool to predict emotions based on facial expressions. To run the code, we must first modify the configuration file, which is used to set dynamic parameters. Some of the important parameters are the model type, is Raspberry Pi camera, and input type. Using the model type parameter, you can choose between CNN and 3D CNN. Currently, it is set to 3D CNN. To run it on the Raspberry Pi, set the is Raspberry Pi camera to true. It is set to false as I am currently running it on my laptop. To use the camera as input, set the input type to camera or set it to video if you wish to use a pre-recorded video. I will demonstrate using both. We will now watch the video we will use as input. As you can see, she looks happy. Let's see what the tool thinks. We will now run the tool using this as the input video. As you can see, the tool too believes she is happy, with a probability of 0.99 for happy. You can also see the other emotions and their probabilities. We will now run the tool using the laptop camera. To do this, we would first have to edit the configuration file and set the input type to camera. Let us now run the tool. At the top left of the screen, you will see a histogram that represents each emotion's probability. As you can see, I look happy and the tool has predicted the same. I will now change my facial expression. The tool will now use this expression as input. The tool now predicts I am sad and fearful. The prediction is also printed on the terminal. This brings us to the end of our demonstration. Thank you for your attention.
That's all for the video demo. Now we are going to explain more about the audio module, and it will be explained by my colleague, Luis.
Thank you, Yusril. I'm asking for request now. So hello, everyone. I'm Luis Roma Barge. I am the software architect of the audio team, and here I'm going to explain how we implement the pipeline in the audio team. First, I'm going to explain the dataset we use for training. Then I'm going to explain the process of the data wrangling. And finally, I'm going to show the AI models. First, with the dataset. In the audio model, at the beginning, we decided to implement two different models, one based on the tone and one based on the text. This is because there is emotional information not only in what you say, but also in how you say it. For the tone model, we decided to train with the Raptors dataset, just like the video team, and with the test dataset. The test dataset is a dataset from Canada. It's composed by 200 examples performed by 2 actors. For the text model, we decided to train with these 3 datasets, MEL, ICR, and Tweet. This is because the number of sentences in the Raptors dataset is quite limited, so it's not possible to train a text model with those. After some weeks of working, we observed that we were not obtaining promising results for the text model. Basically, the text model was not able to predict accurately based on plain text. If you think about this makes sense because when you receive a message or an email, it's difficult to understand the emotion of the person writing it. So after some investigation, we decided to stop working in the text model, and we found some papers that support our decision. Then again, we moved to fully, all our efforts were focused in the tone model. Here I'm going to explain how to pre-process an audio signal to train a neural network with it. After some initial research, we found that the male frequencies central coefficients here are the general way of training a deep neural network with AI. Sorry. Yeah, for the what we do at the beginning is what we call duration equalization. This consists in adding silence when an audio file is not long enough. After this, we execute a fast Fourier transform, and I'm not going to go much into detail. This consists into taking an audio signal from the time domain and moving it into the frequency domain. After this, we execute another transformation into the MEL scale, and we apply a logarithm. After applying a logarithm, we obtain this midterm result called log-Finterbank energy, and I will explain later what we use this for. If we apply another fast Fourier transform to the log-Finter energy, we obtain these MEL frequency septal coefficients. These coefficients give information about the phonemes in the vocal tract, and all the information regarding the frequency of a sound is in these coefficients. Now I'm going to explain both models that we developed for the tone. The first model we developed is what we call the sequential model. This is a model that we developed in the first weeks, so it was like an exploration model. As you can see, the model consists in 3 groups of convolutional one-dimensional layers with a batch normalization and a dropout layer. After each of these groups, we have a max pool in 1D, and then we have some dense layers for the output. The input of this model are the MFCCs, and the output is the 5 sets of emotions. So we can predict these emotions: neutral, happy, sad, angry, and fearful. Once that we had enough experience about how to deal with this audio deep learning model, we decided to try to implement one of the state-of-the-art papers, one of the state-of-the-art papers that we call a Siamese model, and we succeed. We call it Siamese model because it has 2 branches, and these branches are equal one to each other. In these branches, you can see that we use 3 groups of convolutional 2D layers with batch normalization and max pooling also 2D. After each of these groups, we have a spatial dropout layer 2D. These both branches are equal. The only difference is that one of the branches takes the MFCCs and the other branches takes the log-Finterbank energy. The results of these branches are concatenated in a concatenation layer, and in the same way we obtain the 5 emotions that we previously talked. Here I'm going to show a small summary comparing both models. On a side note, we develop and deliver both of these models to ESA only to prove that in our system it's easy to integrate new models. So talking about complexity, the sequential model is more simpler and the Siamese is more complex. This model, as you can see, the Siamese model has more layers, so also has more operation and a bigger computation time. Still, the prediction time of the Siamese model is under 1 second, while the sequential model was about 3 milliseconds. On the other hand, the accuracy of the Siamese model is better, so we reached a validation and test accuracy of 69%. Other difference is the input, as I explained. The sequential model only requires the MFCCs, while the Siamese model requires the MFCC and the LFE. Regarding the model size, both models have a similar size, but the sequential model is a bit smaller. Now that I show you the general pipeline of the audio, I'm going to show you a video demo of the audio module. In this demo, we will see how to configure the system, how to run the system, and how the system shows the prediction result. As I know, the numbers that you are going to see are the confidence value of each emotion, not the accurate value.
Welcome to the demo. In this video, we will show you how you can use the Stern Audio tool to predict the emotions based on the tone. As you can see, we use a configuration file to set the dynamic properties such as the model direction and model type. By using the command line and specifying the configuration file, we can start predicting. Normally, the tool uses the system's microphone, but now, for this demonstration, we are using tool recorded audio.
Stay away from me.
As you heard, this audio represents fear.
I told you, stay away from me.
And this one is the angry one. Now we are going to run the script. It is also good to mention that this model is the Siamese model. Based on the results, the fearful audio contains 58% of fearful, 20% of sad, and 2% of neutral emotions. Also, for the angry audio, the model recognized 60% of anger, 35% of fear, and 3% of happiness. In the next part, we will predict the audio files based on the sequential model. To work with the sequential model, we should change the model direction to refer to the sequential model directory and change the model type to sequential. After that, we run the model in command line again. This time, fearful audio results are 93% of fear, 4% of anger, and 2% of sadness. For the anger audio, we also have 95% of anger and 4% of happiness. Here you can see both results of Siamese model and sequential model together. Thank you for your attention.
Thank you. Now I'm going to give the word to my colleague Chris.
Thank you, Luis. Okay, so now that we have an idea about how the training is conducted in the pre-processing steps, we can look at how do we bring this all together. So again, we have our initial data sets, we do our data wrangling, and our AI modeling. So combining this video and this audio, we take this original data wrangling or the pre-processing steps and the model training, and we get the best results of each. So now that we've identified the best pre-processing steps that we can do and the best hyperparameter tuning and feature extraction we can do, we want to deploy these. So we take the best versions and we put them onto our Raspberry Pi. Now the Raspberry Pi has some sensors that are running, which in our case is the microphone and the camera for audio and video. And it's actually detecting an astronaut or a person while they're conducting their test. It's going to take in this input data, do its pre-processing, run it against the model, and it's going to hopefully detect the emotion that we're looking for. Finally, it's going to display, for example, as you saw in the demo, a histogram that's going to show the different distribution of the emotions on the face, or also some logging for information. This is going to contain the emotional state along with the confidence value. So this information will be provided to either the user or additional systems in the future. So that basically covers the high level and some of the maybe lower level details of our system. At this time, I'd like to give the floor over to George for verification and validation section. He will talk more about the testing components of the Stern system. Thank you.
Thank you, Chris. Hello, everyone. My name is George Aziz, and I'm the test manager of this project. Let me start by providing you with an overview of the project, but from the perspective of testing. As we have mentioned already, we have two different systems. We have a video system and an audio system. And these systems must perform certain functionalities. Some of those functionalities are exactly the same. For example, both of the systems have to perform a prediction of the emotion, and this needs to be fast and accurate. They have to display the results, and they also have to store the results. However, we also have some functionalities that differ. For example, the audio system must perform frame extraction and frame storing, and it also must perform face extraction, which involves face detection and image cropping. And the audio system must perform frequency extraction. From a testing perspective, these functionalities vary a lot. For example, on the one hand, we have face extraction and frequency extraction. And these functionalities, they have specific requirements that have to be met and verified. And on the other hand, we have the prediction of emotion, which does not. This is the basic difference between the native components and the AI components from the perspective of testing. And our systems consist of both. The native components have specific requirements that can be verified, and they have to be verified. Whereas the AI components, they have some specific requirements, especially for interfacing, but they also involve a continuous assessment for the candidate models. As a test manager, my goal was to produce a procedure such that we can address both of these concerns. What we did was research in order to find what the best practices are such that we can tackle these concerns. For the native components and the verification of requirements, you can implement unit tests, system tests, smoke tests, and integration tests. Whereas for the AI components, you have to work with statistic metrics, which provide you with a description of the behavior of your model, such as accuracy, performance, F1 score, confidence, and others. After that, we decided to do an assessment of those best practices so that we know which are the best fit for our project, and we decided to do the following. For the verification of requirements, we decided to implement unit tests so that we can verify the behavior of our classes and of our methods, such as face extraction, for example. We decided to perform system tests so that we can verify the behavior of the complete system, and we implemented scripts that perform smoke tests so that we know that the core functionalities of our systems are in place. For the AI components, we decided to work with the accuracy, the performance, the F1 score, the confidence, the per class accuracy, and the per class confidence. Up to this point, I have talked to you about what concerns we want to address and what best practices we are going to use in order to address these concerns. Let me now describe your solution and what technologies we use. First of all, we wanted to work with industry standards. As a result, we decided to use GitLab in order to manage our source code. However, GitLab is not efficient with large binary files. For that, we decided to work with DVC, and we integrated these two services. We use Docker for our building environment, and we build two different conditional pipelines. Each of these pipelines addresses one of the concerns that I mentioned before. These pipelines run on hardware, and we are using the Raspberry Pi, which is the platform that we will eventually deploy our system, and the TUE infrastructure for convenience purposes. Now, let us dive further into the conditional pipelines. On top, you can see the pipeline which assesses the AI components, or if you will, the continuous assessment of candidate models. And on the bottom, you can see the pipeline which assesses the native components or the verification of requirements. Let us start with the second one. As you can see, this pipeline consists of three different stages. On the first stage, which is called PEP8, we want to make sure that we want to verify that our code complies with the Python quality standard PEP8. On the second stage, which is called unit tests, we run the set of unit tests that each team has developed. And on the last stage, which is called smoke tests, we run the scripts that perform smoke testing such that we know that the core functionality of our product is in place. Both of the teams had to develop certain test cases. The video team developed 20 test cases and all of them pass. And the audio team developed 12 test cases and all of them pass as well. The system tests are done manually. The reason we chose this approach is because automating system tests for such configurable system can be very time consuming. And since this was not a repetitive task, we decided to allocate these resources elsewhere. On the bottom right of your screen, you can see two traceability matrices, one for the audio team and one for the video team. The purpose of these matrices is to map every software requirement to the test case that verifies this requirement. And it is important to say that we verified every implemented software requirement that we had. Now let's continue with the AI components and the continuous assessment of candidate models. As you can see here, this pipeline is significantly bigger. We have 5 different stages. And on the first stage, what we need to do is we need to fetch our candidate model and our testing data from DVC because GitLab Runner is unaware of this data. After they are cast, we can continue with the next stage, which is called data. Here we run as a set of test cases against our testing data. This may sound a bit odd for people who are not data scientists. However, you can think of your testing data as a piece of software that evolves over time. You may add new data, and you may have some things that you want to verify. What we do here, because our project was very small, we just verify that our data are of the correct type and of the correct size. The next stage is called interface. Here, we are verifying that our candidate model interfaces correctly with both native components. And this is done via another set of test cases that assess the input shape and the output shape of the model. The next stage is called thresholds. And this is a very interesting one. In this stage, we have developed a generic script that loads the candidate model. It also loads the testing data and performs an assessment of the model based on the statistic metrics that I mentioned before. The output of this script is the JSON that you can see on the bottom left of your screen. Once we have this assessment, what we can do is a comparison between our candidate model and our deployed model. And this is done again via a different set of test cases that we developed, and you can see them on the bottom right of your screen. In this case, all of the test cases pass. And this means that our candidate model is actually better than the deployed model, and as a result, we should redeploy. But before we do that, we run the last stage, which is called smoke, and it performs some smoke tests on the product, but with the candidate model, such that we know that the core functionalities are still in place. The reason that I'm very proud for the work that we put in this pipeline is because it is very generic and very configurable. It doesn't have any hard dependencies, and as a result, it is extendable, and you can easily integrate it in other AI projects. Imagine, for example, that you are working on a project where you have to develop a certain neural network that performs some sort of classification based on a predefined set of categories. In principle, you can easily integrate this pipeline into your project and perform this continuous assessment of candidate models. At this point, I would like to thank everyone from the team that worked on the testing aspect of this project, and especially our configuration manager, Jorge Codrero. That was all from testing, and I will give the word back to Juan. Thank you.
Yes, thank you, George. All right, I think we've gone over all the technical details so far. And to wrap up the presentation, I want to give some findings of ours. I want to give a summary of all the value that we have provided and some future recommendations. Starting with the findings, these are things that we found interesting in our project and that can be of value in future projects. In the video pipeline here, we see that emotion recognition on grayscale images gave better results. And this is really something that's interesting to us, since normally you would say colors images give more data, and more data means better results. But for us, grayscaling the images really gave us better accuracy and better results. So that's an interesting point. The second point is that emotion recognition on larger images didn't necessarily give us better results. We tried it, for example, with 32 by 32 pixel images and with 100 by 100 pixel images. And for us, the result didn't really change. So in that sense, adding more data didn't help the case. Of course, you can't say anything about full HD pictures or other sizes, but for us, increasing the image size didn't affect the results. Then for the audio part, dealing with different accents is difficult with audio emotion recognition. We were very limited in our choices of data sets. So we went with the reference data set, which is also very North American based. It has a very North American accent. And we also created our own data set, and we are a very multicultural team, which caused to our accuracy dropping a lot because everyone has a different way of pronouncing things. And our model couldn't really deal with that. So that's something to take into account for any future project, that if you are dealing with different accents and you want to deploy it with different accents, then you should also reflect it in your data set. Then on the last part, it's the distribution of the data set is important for a high fidelity approach. What we mean by that is what we already presented earlier. Chris presented that, is that we have a data set based on percentage, and then we have a data set based on actors. And in the percentage, we train and test on the same actors. And in the data set based on actors, we train and test on different actors. And we think it's quite important that we use a high fidelity approach here and that we go with the data set based on actors. We already saw that the numbers for the data set based on percentage were much higher. They were even in the 90% accuracy. However, during training, you have already seen these faces, so these numbers are not really representable for what happens in real life. And I think what we have done with separating the data set and actors, we have really went with a high fidelity approach here. So summarizing the value that we have provided ASA, first of all, we developed an extensible and modular AI pipeline, which is also according to the requirements we set ourselves in the beginning of the project. The second point is we've identified challenges and use cases in deep space. The third point is we have classified audio and video with a high fidelity approach, also because of what I just told you. And the last point is that we conform to the ASA standard for documentation and modeling. And this is quite important since software can often become quite complex, and just commenting the code and being structured doesn't always help. Therefore, we went with the ASA standard for documentation and modeling, such that ASA always is familiar with the work that we deliver them. And we really value this. So what about future recommendations? These are recommendations from us as a team to ASA to work on in later stages. The first recommendation is to use the landmark feature for the video module. What this means is we don't use just the cutout face as an input for the model, but we actually identify certain landmarks on the face. As you can see in this picture, the eyebrows and the mouth are labeled and dotted, and use that as an input for our model. In that way, we can see certain changes of the position of these landmarks. And for example, if someone is smiling, you can detect that in the model. And we think this is really valuable and something to look at. The second recommendation is using a multimodal system output fusion. What we mean by this is for now, we have provided ASA with a video pipeline, and we delivered them separately, and they both have separate output. But by using a multimodal distribution, we can merge these pipelines and get to one final result. And we think using both video and audio, we can get better results about the emotion detection rather than doing them separately. Then the third and fourth recommendation. First, the input for a recommender system. We recommend to use our output of our assessment system as an input for a recommender system. What we mean by that is it's of course not only important to assess a certain emotion, but also how to deal with it. So with a recommender system, what we mean is a system within the spacecraft to give advice to the astronaut how to improve their negative emotion or how to stay in their positive emotions. And then our last recommendation is to use more sensors than just the video and audio sensors that they use right now, but maybe some EEG sensors or heart rate sensors can be very beneficial for the accuracy of the output of emotion detection. And we think the heart rate and the brain waves also have to do with emotions. All right, we've come to the end of our presentation, but not before I thanked a few people. First of all, I want to thank our whole PDEng software technology team. You can see all of our faces here with our appropriate roles. Further, I would also like to thank our program director, Janja Dijsuren, and our secretary, Desiree van Oorschot. I also want to thank all of our coaches that helped during this project. We have really nice PDEng coaches, and they were of great support. And last but not least, I want to thank ESA, and in specific, I want to thank Luis Mancia and Christoph Hanwald for their support and being our direct supervisors. And with that, we've come to the end of our presentation. I've really enjoyed this. I've really enjoyed the whole project, and we're open for any questions. But at this point, I would first want to ask Claude Nicoyer if he wants to do a few words for us. Claude is a retired astronaut. He spent over 1,000 hours in space, and he's a great contribution to this presentation if he wants to take a few minutes for us. Are you here in the call, Claude?
Yes, I am. Hold on a second. Okay, I am. Well, thank you very much to Luis and Juan for really interesting presentation. I did not follow in detail all the technical aspects, but I would like to congratulate the whole team because I know that this is a lot of work that has been done and you've got results, and congratulations. I have a question whether this is going to be really useful for astronauts. I think there will be a lot of application of what you are doing. It can be for pilots in the courtroom and in different circumstances. This could be really useful to detect emotions and the state of emotions of the persons involved. But you know, astronauts are people who don't like to have too many inputs from psychologists and medical doctors. They want to do their job. And I could detect that there would be a lot of resistance by astronauts to have anything done in this direction. And again, this had nothing to do with the high value what we have been doing and the wonderful achievement that you reached. But you know, people tend also, that's not astronaut only, but tend to hide emotions. You know, you may be sad or you may be worried, but you want to look good, so you smile. And how do you detect the ability of hiding emotions? Is your AI system smart enough that it can detect the hiding of emotion by anybody, whether it's an astronaut or another person? Now, another thing is specifically for astronauts, we tend to repress emotions and do our job. Except if we have some problems where the emotions are operationally significant. Let's say you want to undo a bolt and there is no way to undo it. So although you went to the maximum torque allowed for undoing this bolt, but then if it is operational, then you share it with others. No barriers. You try to be transparent because we try to solve this problem. And if it is during a spacewalk, for instance, there is limited time. Then you share it. I think in general you would tend to hide emotions, except if it is emotional. Excuse me, if it is operationally significant. In this case, you are transparent and you share it. Another point I wanted to mention is that if you want to gather a baseline for astronaut, because obviously for each astronaut, you would have to gather a lot of baseline data, and this would take time. And the astronauts are really busy during their training, and I'm not so sure that they would be willing, the astronaut themselves or their supervisor would be willing to devote the time for that, to create the database, because for each person, you would have to create a solid database before using your system. Another point I would like to mention is that emotions are pretty significant during spacewalks. As long as you're in the cabin, you are in a pretty safe environment and you have your other people around you, and if there is anything, you talk freely and it's a more relaxed environment. Stress comes more in spacewalking than it does when you're inside the spaceship. And of course, if you are spacewalking, then the video will be very difficult to get because you have this very small volume of the helmet. And the audio would be a way to get emotions, but the video, I doubt it. Now, if ever there are data collected about emotions of astronauts during a space mission, whether it's when they're inside the cabin and in a stressful situation, or whether they're outside spacewalking, it will be very important to not disseminate this information, but to get the information directly to the crew surgeon. The crew surgeon is a position within the Mission Control Center, and the crew surgeon talks directly to the flight director. The flight director can then ask the Capcom to voice a message to the crew, but it would be a disaster if any of this data would be open and the press people would immediately gather it, and then you have the headline in the newspapers the next day. So confidentiality of information related to emotions of astronauts is very important. These are my general remarks, and of course there are a lot of points there, but the first one I mentioned, that people tend to hide emotions. I don't know what you have to say about this. Can you detect if an emotion is being hidden? Is your software, your AI system smart enough that you can detect if somebody is hiding something? And this relates also to the use of this system in the courtroom. Could it be maybe a lie detector system? These are open questions. These are my comments.
You want to take up on them, Chris?
Sure. So one thing to note about the system that we've developed is it's completely a proof of concept system and a feasibility study. So the idea is it possible to receive these results? One of the suggestions we gave for future work is to incorporate EEG or electroencephalography sensors. It's a lot harder. It's a lot more difficult to hide certain things like your heart rate or the waves going through you. So we would be asking the astronaut to be connected to different type of sensors at all time, and we also know that astronauts don't like to be connected to sensors all the time, right? They get in the way of doing your job. But if it were possible that they could wear some type of suit at a certain time, or if you had an undersuit in your when you're going on an EVA, for example, in your spacesuit, then it would be able to probably a lot harder for the astronaut to hide their physiological response. So this would be something in future work, if this was interesting to try to help astronauts on deep space missions where they can't just talk to the MCC or to ground. They don't have the surgeon that they can talk to. It might be interesting for us, we think, to analyze the astronaut in these deep space missions where more autonomy is needed.
Yeah.
Yes,
Okay.
and
Sorry for interruption. I also see a comment from Alexander, and I think that's a very nice remark. I think, Alexander, you can also step in, yeah, and elaborate on the hidden emotions and the identification of micro expressions.
Yeah, so thank you very much, Yanja, for giving me this was a word. So indeed, I mean, there are all kinds of ways of trying to detect hidden emotions. There isn't theory of micro expressions. Micro expressions cannot be controlled. We usually do not observe them because they are so rapidly passing. Of course, if you have a video recording, you might detect them and you might analyze them, but the problem is that micro expressions are kind of controversial. Using biometrics as suggested by Christopher is of course another possibility. However, most of the biometric measurements are quite invasive. So essentially when you are asking a person to wear EEG, an EEG screen, which are measurement thing, right? you will typically say, you cannot work because it's not combinable, and not even to offer astronauts, even for regular office tasks, it's becoming problematic. So in a sense, in our recent work, we have used a wristband. So a wristband which is using, which can measure, for instance, things like galvanic skin response. This is much more limited as a data source. And the results are not, spectacular in terms of detection, but at least it's much less invasive than what you would have with more advanced biometrics.
Yeah, very interesting. And I think people probably know Claude Nicollet has done the first spacewalk from ESA's astronauts, right? I think I was just checking.
Yes, I did one in December 99, doing some repair work on the Hubble Space Telescope together with Mike Fole, my colleague from NASA. We exchanged the main computer of Hubble and exchanged the fine guidance sensor also. It's a kind of a pointing camera for the telescope. So, yeah, I was exposed to the spacewalking situation, and again, in terms of emotions, whether they are positive emotions because of the unbelievable experience that it is personally to go spacewalking, or the potentially negative emotions in the sense that you may be worried you have much less protection, physically speaking, than you have when you are inside the cabin. You have much less redundancy in your space suit compared to the redundancy of, let's say, the International Space Station or the Space Shuttle. So in a way, it's you feel exposed and in a risk situation that is definitely much higher than when you are inside the cabin. But again, I mentioned that before, and that's important. You have to do your work. And spacewalking is always limited in time. It's limited to about 8.5 to 9 hours maximum. Ours did last 8 hours and 10 minutes because we have with a number of problems to insert the new fine guidance sensor into the telescope. But again, you train a lot. And as you know, if you are well trained, you reduce the level of stress and emotions. And that's a very important factor, reducing stress. The best way to reduce stress is to be well prepared, not only for the nominal operation, but to cover a number of obstacles and problems. And we had a number of them, and we were not worried. Well, we were somewhat worried we couldn't complete the task within the 8.5 hours maximum for the spacewalk, but we had the help from Mission Control Center. We had help from the astronaut inside the space shuttle. We were discussing these three entities, the astronaut spacewalking, the personnel inside the cabin, and the mission control center. And we try to stay calm and solve the problems with serenity, never getting too nervous, just solve the problems. And we are trained to act in this way. I always take the example of Apollo 13, bang, explosion of an oxygen tank close to the moon. And 30 seconds later, Houston, we have a problem. And, and that's showing very little emotions. I don't know, it would have been interesting to see his face and maybe analyze in detail his voice when he said that. But we tend to repress emotions and stay calm, even in very critical situations.
Right. I think Claude, very nice insights actually about the future research directions. I think because especially indeed controlling the emotions, astronauts are master about. So these micro expressions are quite difficult. I think. I see there is also a question from Cecilia. I saw Chris has answered, but just in case people haven't read the comment section, perhaps Cecilia, can you raise the question?
Yeah, sure. First, maybe I introduce a bit myself. So I'm working on the ISS operation for the ESA part. And yeah, I was wondering if you have looked at the Simon experiment. So this one was a first trial of, I think, yeah, a bit of artificial intelligence Yeah, the main objective was to have a sort of companion for the astronaut. But in one of the latest run with Luca Parmitano, some also of the feature that this experiment had was to look at a subset of moods of the astronaut. And yeah, that was the question. What I wanted to say or add or making echo, let's say, to what also has been already said, is that for the astronaut, you always need to have a consent to agree to sort of type of experiment, especially human physiology, and in this case, related to to what is in the emotion part. Yeah.
Yeah, and I guess you can expect that there will be quite a lot of resistance. I know astronaut,
Yeah.
I was one of them. But maybe in some cases, an astronaut will accept to be kind of a guinea pig for testing the system. But in general, there will be resistance of astronauts to be subject to this.
Yeah.
Right.
As a side note to that, like Simon's, for example, a great example on whether affective computing, which is this kind of area that we are talking about here, can be of help. And we actually look at Simon, and we believe, for example, that at the end, the Simon was a technological demonstration. So we want to how to enhance Simon in many ways, and this is one of the directions that it could go.
Good.
And it also raises a really interesting question, which hasn't been addressed directly here, which is going to be the interaction between the machine and the human. It's going to be a one-to-one interaction or one-to-any. So because here everything is presented as a data set and we have videos, but how is this interaction going to actually happen in a real scenario is something that, of course, if in possible future development we need to address and decide, because it will also drive the design of the final system.
Right.
Yes.
Yeah, indeed. Oh, sorry.
Sorry. Yes. So as Mr. Nicholas said, I think the acceptance by astronaut may be the most difficult point related to this technology. And for sure, we have to consider that the data have to be secured and distribution limited. At least the result should be limited to the astronaut himself, so it should understand that it is an help to him, an help to his manager, most probably, and provide useful feedback. So this is something that may help to accept this kind of system. But of course, it will require, let's say, some work to ensure those two aspects.
Yeah, but very good research.
I think typically it would go to the astronaut and the crew surgeon. Again, the crew surgeon is really a big help, and there's a very good trust between the crew surgeon and the crew members, and the crew surgeon is there to help the astronaut mentally and physically to do his or her job. And I would imagine the data going to the astronaut and to the crew surgeon exclusively, and possibly the crew surgeon could share with the flight director, who is the big boss of every space mission. As you know, it's not the commander on board, but it's the flight director in the control room. But the distribution of the data related to emotions of astronaut, whether it's voice or images, should only go to a very limited distribution. The astronaut, the crew surgeon.
Yeah, and also as a comment to that, I think thanks again for the really helpful insight on this. And it's important to notice that I think we already mentioned that this is a really exploratory analysis. Further activities, we should include physicians and psychologists here. So maybe to identify other possible goals for a system, not only identify these 5 emotions, but maybe just something more simple, whether someone is under a real stress or not, just detecting the peak of stress, it would be useful. So understand this study as this nice preliminary study, but a most heterogeneous team should be gathered in order to get something more, let's say, more applicable.
Yeah, I think a lot of constraints indeed when it comes to the astronauts. I could also imagine from the PDEng side, for example, we keep track of the emotions of our trainees. So in terms of happiness level during the training projects, of course, we are not astronauts, so but still there is, I think I tried once to apply open platform to, so the camera on their laptops could detect their emotions, but I encountered obviously quite strong resistance. So I could imagine the same applies for the astronauts. But I think indeed a non-intrusive and a solution that doesn't intervene with the focus and work of the astronaut seems to be important. Yeah. By the way, I think we are in a question and answer session. Anybody who wants to raise a question, you can just open your camera and raise a question. Also, you can ask from Claude or Christophe and Luis at the PDEng team. I think everybody who presented and Luis, Christophe, I think we can go online. Also Claude, because I think we don't have risk of losing the slides by now. Any questions?
Shall I stop sharing the slides then?
No, keep it. It's okay. Yeah, it's not eating much bandwidth. Yeah. So let's see.
I'm Alex Donati.
Yeah, Alessandro, go ahead.
Yeah. The question is the following: is for Claude Nicolier. Can we envisage the utilization of such tools not only during the real flights and operation, but particularly during the astronaut training? And if yes, for what you would use these techniques and this approach?
Yeah, I guess that we could, because again, the training is there in order to prepare the astronauts to a high level so that whenever they are up there in space, whether they are in the spaceship or whether they are spacewalking, they understand what they have to do and they understand the technical aspect and operational aspect of what they have to do sufficiently that they are in a calm and serene position. And even if they have some problem occurring, very often there are problems that they've been exposed to during the training, and they stay calm because they know a solution. And if they have a problem that is not covered by their training, they are so accustomed to face problem because during training you have problems all the time in order to prepare the astronaut to face adversity and still accomplish the mission. I think it could be useful during training to see what situations, typically a difficult situation or technical problem or semi-catastrophes, drive emotion to a high level. Because when you are training in the simulator in a rather high fidelity system, technically speaking and operationally speaking, you feel that you are really in the mission. And there, the first time you're exposed to a loss of cabin pressure, for instance, whether it's in the shuttle or the space station, it can drive emotions quite high. Although it's a simulation, you feel that you are there and you are really faced with a big problem that could kill you if you don't do the right thing. So possibly it could be used maybe even better in training to see what are the situations, technically speaking, that drive a lot of emotions among the crew, a lot of stress, and that require more thorough technical preparation in order for the crew to stay calm despite the severity of the problem. That's a good comment.
Yeah, I think it is also important to do that during training because it will highly improve the quality of the results. If you, let's say, take the feedback of the astronaut after the capture of the image and audio during the training session and you ask him his feedback on what he felt during the training session, then you can really improve the accuracy of the system. And during a real mission, then you will have very good result and good help to the astronaut.
Yeah, and I think it will be much more accepted by the astronaut also, because typically in training, it goes to the training team, to the astronaut, to the training team, the flight director, and maybe the person in the control room, but it doesn't go to the outside. Unlike during a space mission itself, it tends to go to the outside. It's very difficult to hide. So that's a good point. I think the acceptation level would be much better during training, and it would be useful to detect the areas where the crew needs more preparation to stay calm despite the severity of the problem. Good point.
All right, thank you for the insights. Are there any more questions to anyone here? No more questions? You can just pop up your camera or turn on the microphone.
Okay, if there are no more questions, then maybe we can just to
Wrap up.
finish. I wanted to say that anyone that if you have any further question, or for my colleagues also in ESA that you are doing currently some similar research, please, you can always contact Christophe or myself to see whether we can do a follow up on this activity some ways. And we are really keen on, of course, having the feedback of, as I said, physician or psychologists from the astronaut crew management team or other team involved with similar activities, because that will be crucial to have something that can be really used.
Luis, Cecilia here.
Hi, Cecilia.
Hi. Yeah, on this point, I think, I mean, you should contact then our ESA astronaut crew training. And yeah, I think, I mean, the point of training is a very good one, and where you can see some application of this research. So
Thanks for the
yeah.
feedback, Cecilia. Thank you.
I see it even as a primary utilization of what you are doing in training more than during the mission itself.
Yes, I think we will involve the training team in the next step.
Hello, Christophe? Christophe, okay.
Yes.
Okay, I thought we lost you. Yeah.
Okay, then I think.
Yeah, Luis, by the way, I think from our side, the TV side, about the follow-up or any contacts, of course, we will provide you contacts with our scientific staff and researchers or professors who are doing the research in the same area can contact you directly. So thank you for pointing that out. And Christoph and I, we will have a flying meeting afterwards later on to discuss maybe related or other potential design projects. Yeah, and I think we are coming to an end, right, Juan?
Yep.
Yeah. So I think before we close the session, Luis and Christoph, the ESA team, we really want to thank you for a very exciting project, especially in this pandemic time. It has been a pleasure from our side to work on it. It was fun. It made our life, I think, really exciting. Our trainees had really good time. This was one of the rare projects where our trainees' happiness level every week was constantly above 8 in a scale of 10. I don't think they were lying to me, but there might be some hidden emotions involved. But it has been such a joy for our trainees, and they have also learned a lot, because indeed, as Juan has mentioned, in this 18 team, there are only 2 AI engineers, and they also learned a great deal from you, Luis and Christoph, and of course from our coaches. So some of our coaches, experts are in attendance, as well as as you can see. So we also want to thank our coaches and scientific staff for providing the know-how and also the advice for our trainees to make this 10-week project successful. As you all know, in the PDEng program, we hire the top talents from around the world, and we prepare them to work in a highly pressured situations and deliver good results. We are very pleased with this training project results, and we want to thank again for our team members, the PDEng trainees as well, and also want to wish them their individual final projects that they will start in January. So I think, and also again, Claude Nicolet, we are very happy to meet online with a real life astronaut, and also thank you for sharing even briefly your insight, because of course, you know, from our side, the practical point of view, we don't have 10 weeks. It's not enough time to do stakeholder analysis having an astronaut, but at the end, on our future work, you have given really insightful and good feedback, which I'm sure triggered some thoughts and directions. So thanks a lot. Yeah, and so we are also very honored to join. To welcome you here as well. So I think from our side, this is it. Christoph, do you want to say a few words? So.
To unmute. Yes, of course, I would like to thank you, Yanya, and all the team, the PDEng team, for the excellent work that has been performed, because it was a very short duration activity. So taking also into account that actually it was 2 projects in one, because you had the audio and the video streaming analysis. So it was quite challenging, and I think a lot of work has been done. And it will, let's say, of course, help us to continue on this type of activity. And it will provide a lot of work to Luis and Diane, who will, let's say, take now the result and try to build on top of it. So as we mentioned, involving aSTronaut team, but also looking at the, let's say, different algorithms, and also implementing the recommendation you provided. So we will take that, and we hopefully we'll be able to initiate activities to implement real systems that is based on this work. So it was really, really good result from the team. So thank you all.
Thank you, Christoph.
Yeah. And from my side, just to add, highlight Christoph comments. Thanks for the hard work, given the 2 months activity. And it's also been a pleasure to work together with you. So congratulations.